front, left, front, right.
Richard, can you hear me? Please mute yourself, Richard.
Yeah, can you hear me now?
Yes, I can.
Okay.
Yes, sir.
And you can see my slides?
Yes, sir.
Okay, hopefully this should work. Okay, so now we want a sorting algorithm where in a read-only memory, input is given. In a read-only memory, you can only pick up things, do some comparisons, use some small space, and output. So can somebody give me a sorting algorithm using constant extra space? So that's my model where you read, do some comparison, there is a small working space, and you're allowed to output into your thing. So now give me a sorting algorithm in this model using constant extra space.
A bubble sort or selection sort?
Bubble sort, you're going to move things around. You are not allowed to move elements within your array.
Oh, okay.
Okay, good. Find minimum element and print. Okay, and then continue, I guess, right? Yes, repeat. Find minimum element, output, repeat.
Yeah, what I mean is that next time we'll find the second minimum element and so on. We can still mark things, right? It's read only, but we're not allowed to move them, but marking is still fine.
No, you can't mark them. What do you mean they mark?
Like we can remember in some way that, okay, we have to enter the minimum element. So
okay, first I'm glad you at least realize that that's important, that we need to remember the minimum element, because if you don't do anything, you find the minimum output, and then when you go and find the second minimum, the same minimum will come. So somehow you have to remember something. But if you remember that space, that's accounting for space. How much will you remember?
N.
Yes. So I want to do constant space. Not very hard. I mean, you can just think a little bit. So I find the minimum, output it.
So store the minimum element in a variable.
Minimum element, okay.
And compare it. We have to find the minimum element, and we have to compare with the previous minimum. And
okay.
if it is greater than the previous minimum, we output it. Else we ignore that because we have already printed that.
Okay, that's the second step. What do you do for third step? What do you remember? How much?
So maybe
the current minimum, sir.
Yeah.
So maybe we can store count alongside minimum.
What count?
Count of the current minimum that we have already stored in the array.
Okay, but think a little ahead. How much will you? I mean, this is all okay for your first step, and then what?
Sir, we can
that
store
will take login, right? Yeah.
We can store the previous minimum element, like the minimum element of the previous iteration, and find the element immediately greater than that, and we can keep repeating that.
Okay, good. So the algorithm is keep finding the minimum is fine, but the problem is you don't want to repeat. So I find the minimum, output it, and remember the minimum in this iteration. So that's only one value. Now, among all elements bigger than this, I output the minimum. And remember this new minimum now. Among all elements bigger than this, assume all elements are distinct. Okay? Otherwise, you can count and output the count. Suppose the minimum element appears 5 times, you can find that and output 5 times and 0. That's just one more pass. Okay? So assume all elements are distinct. You find the minimum, output it, and store the minimum. And then among all elements bigger than the minimum, output the smallest. Store this new minimum, continue this. Okay, you see that it's already the problem is becoming interesting and complicated, right? It's like you're doing sorting with your hands tied at the back. Okay, because you're not allowed to move elements, you are not allowed to use a lot of space. So an n-square algorithm using order 1 space is repeatedly find the ith smallest. In ith pass, you'll find the ith smallest, but you have to just keep track of the largest element you have output so far, which is basically the minimum in the previous iteration. So is that okay? Put +1 if you understand it. Otherwise, put -1. So we have an n-square algorithm to find the sort from a read-only memory. Good. Okay. So now, suppose, can I generalize it? Suppose I give you not constant space, some S space. Then how much, what can you do? Okay. So here is an algorithm. Again, you can think about it, not very hard. So I keep track of S elements at a time, not just one element. So what do? I find the smallest S elements, output them. The next round, I find the next smallest S elements, output them. The next round, find the next smallest S elements, output them, and so on. Okay. So now, how do I find the S smallest elements? I give you S space, and I want you to find the smallest S elements. Let's again assume all elements are distinct to make life easier. What would I do? Okay, Jitendra Joshi says heap. Okay, can you expand on it? What do you mean by that? So, let's see. So here is my array, and I have some S space. I want you to find the smallest S elements from this array. You're not allowed to move anything, mark anything. You can use some order S space if you want, but not more than that. So, Jitendra, can you explain your algorithm? What will you do? He says heap, but anybody or if anybody else want to add? So what do? So let's say I pick the first S elements and put it here and pretend that somehow this is my smallest S elements. Now the next element comes. What should I do?
I should see if there is any element greater than that particular element in S, then we replace it.
Exactly, very nice. So you find, is there an element which is larger than this element? If so, this comes here and that larger element gets out. Okay. And then that's all. You keep doing it, right? Next element comes. Is there an element which is larger than this element? If so, I replace it and put it here. Now, how do I maintain this to answer this question? How do I know? How fast can I find out? Is there an element larger than this? And I want to delete that and include this element.
So like insertion sort, we can keep updating those spaces.
Here is
Like
another
between
problem.
insertion.
Let's say here is another problem. Suppose you find, let's say this is 5. Okay. There are lots of elements larger than this. What should I do? I mean, you compare 5 and say 7. Yes, 7 is larger. You replace 7 and put 5 here. Is that all?
We should try to replace the largest one.
So what do you want? You want
We need to maintain a minimum and a maximum.
Is that enough?
Maybe a maximum in S.
Or a max heap.
Operation we want to do. We want to do a delete max.
Yeah.
And insert. We
We
want to do a
can
delete max.
maintain.
What do you need?
We can math heap.
Exactly. See, do you see, all you learned how you can apply it here, because this is how somebody said. I think Jitendra started with saying heap. So you take your S elements, build a heap on it, build a max heap on it. Now a new element comes, I compare that with the maximum element. If this is bigger than the maximum, I don't have to do anything. Move on. If this is smaller than the maximum, then do a delete max and insert this. So now that's up. We keep doing it. At the end of it, I will be able to get the smallest S elements. I can throw them out and remember again the largest I have output like here, and continue this and keep going. So now let's do an analysis. How much time does this take? Well, to find the smallest S elements, what do? First, I build a heap on the S elements, which takes order S time, right? You can build a heap in order S time. And then for every element here, I'm doing an insert and delete max in the worst case. So that'll be like n times log S, because the heap size is S. So, and for every element, it's actually n minus S times log S, but let's ignore that n minus S, n times log S. And how many times? So this is at the end of it, you would have found the first S elements. And now you do it n over S times, you would have gotten your entire sorted array. This running time is essentially n square by, so to more precisely, let me just say this is order n plus n square log S by S. Okay. Good. So, you see that fun, interesting sorting algorithm. It's just starting from scratch. You don't need any heavy machinery. Well, you need to know heap. So it's essentially like we use S space, it's n square S, but there is a log S, which is not so nice, because for S is constant, we did not need n square log. Okay, it is, okay, it works even for constant, fine. Okay, now I can actually improve this slightly better to n square by S, even get rid of the log S. It works like this, okay? So what do? Write the algorithm. I divide my array into blocks of size n over S. Take the minimum from here and build my whatever I need. So the min of this would be here, the min of this block would be here, and the min of this block would be here. Okay. Now, what is the smallest element now in the entire array? How do I find the smallest element in the entire array?
Minimum of all the S elements.
So I find the minimum. I do a delete min output. A minimum of all these elements might have come from this block. Okay, I don't know. So then what do? I replace it by the next minimum from this block and put it here. And do a delete min output. So insert delete min output, insert delete min output, and keep doing it. At the end of it, I would have got the entire sorted. Okay. Let's analyze this algorithm. So divide the input into S blocks of n over S elements, store the min of each element in a heap, repeatedly do delete min, insert the overall runtime. To find the min of each block, that's order n. Then we are building a heap on these S elements. And then for every element, all you're doing is you're deleting the minimum, finding the next min from the corresponding block, and keep doing it. So this whole thing would be like an n square by S plus n log S. So there is no additional log S. Okay. And world moved on from here. There was another improvement. This was a 1998 Fox paper, which actually even improved it to there is an n square by S log n in the denominator, reasonably complicated algorithm. And we also know a lower bound which matches this upper bound in read-only. So that's sort of the story of sorting algorithms from read-only memory with small space. And what you get is a nice sort of a time-space trade-off, right? If you give me more space, I can actually do it faster. So if S is like n over log n, this whole thing would be like n log n algorithm. And if s is constant, we have an n square. Okay, so some tools you learn about these blocking the array into different blocks, doing thing, using heap, all kinds of things. Okay. Any questions?
Uh, you said that we get the next smallest element from the corresponding block,
Sorry, I
which
couldn't
is
hear you. What?
hello, am I audible?
You are audible, but there is some
Hello.
breaking. You can put it in the chat if you want, or try again. Okay, so it's the whole, I mean, idea clear. You may not necessarily have understood the details, but the whole point is, you know, your hands are tied. You are supposed to do sorting. You can't use a lot of space. Do we need to keep track of which element is coming from which block? Yes, you need to. Good point. Because when you delete the min, you need to find the next min in the next block. So that is another order S if you want it. Or you don't necessarily even need to store these S elements. You just store only these pointers. That's also good enough because the elements are there in your input. So of course you need to build a heap on it. So you can just move the pointers around and so on, or otherwise another S value. So I'm allowing order S space. So yeah. Okay, let's now move on to the selection problem. Okay, so here the problem is I want to find the median or some kth smallest element, not just the kth smallest element, not necessarily to sort. Of course, you can sort and pick the kth smallest element, but you don't necessarily have to do that. The question is, can you do better? So we know, I told you yesterday, there's a classical, this median of median algorithms due to Bloom-Floyd-Pratt reverse target, which gives a classical divide and algorithm. Okay, good question. But if you see, I had a limit on S. So I did not allow S to be going all the way up to N. This trade-off works for S up to N over log square N or something like that. Because beyond that, it doesn't save me much. Because that's a very good point, because you don't want to beat your lower bound for comparison. So it's not N square by S for any range of S. S has a limitation. I can't put S to be N. Good. Okay. Again, I can send you references for this. I have given some references. The slides will be given. You can look up if you're interested. But these are all, important problems. Typically, read-only memory is a model for studying lower bounds, and this n square by s log n lower bound was given way about before upper bounds were given. Okay, let's come back to the median finding problem. If I have no restriction on the time, moving elements, space, and all that, you can do it in order n. As I said, actually, even with space, with constant space, you can actually do median in even 3n comparisons. If you are allowed to move elements within your array, all these work by moving elements. Now, again, there's a very strong motivation, at least for selection problem, about against moving elements. Sorting at least is a problem where you actually want to rearrange your input. But for selection, it seems unreasonable to expect that you are allowing moving elements and so on. And it's possible that this array is used by some other subroutine, so you may not want to move things around, stick them in the order and all that. So let's get on to this model. What we are, you have an array where you want to find the kth smallest element, and you're not allowed to move elements. Let's do some sort of a time space trade-off. This is again a very well-studied problem. There are about 15, 20 papers written on them. So it's easy to get again an n square algorithm using time space. Right? What is your n square algorithm? I want to find an element of rank k. Okay, kth smallest element. Let's again assume all elements are distinct. How do you find the kth smallest element? If I just give you constant space and you are not allowed to move elements in your array. Anybody?
So find the minimum element k number of times, and the at the kth time you will get the kth smallest element.
Okay.
That would be of order of n square.
Or kn rather. Yeah, exactly, right? Order of
Yes.
kn.
If k ranges to order of n, then it would be order of n square.
Absolutely, right. So if k is small, it's good, but if k reaches median or something, you have n square. Yeah. So find the minimum all the time. Okay. Another algorithm would be that I don't necessarily find the median. I take the first element and find its rank. Right? Compare it to everybody and see how many are smaller, how many are bigger. If it's not k, then I just throw it away, move to the next element, and so on. This is also an n square algorithm. So now this is an interesting question. With constant space, can we beat n square? And how much can you do with log n space? I mean, this problem has not been completely resolved, by the way. So what I will give you is an algorithm where you can actually beat n square using constant space. I'll give you an n root n algorithm. You can even improve it into 1 plus epsilon. And this work started from 80. Actually, Monroe Patterson paper is supposed to be sort of the starting point paper for the whole area of streaming. The work happened for 10 years, 20, up to 2013. I've seen papers on this problem. Okay, let's recall how our median of median algorithm works. Okay, so at a high level, here is how the standard linear time algorithm to find the kth smallest element. Okay, where no restriction on space, no restriction on moves, we will not worry about them. First step is to find some approximate median. Okay, I'll explain what approximate means later. For now, what we do is doing with some effort, we will find some approximate median x. Then I'm going to compare all elements with x and count the frequency of those which are less than. So all those which are less than, greater than come here. And you are interested in kth smallest element. So if k is smaller than this number, then you go on a recurse here. Or if k is bigger, then you go on a recurse here. And the property of x is that in whatever you find in the first step is that at least some fraction of elements get thrown away regardless of which side you recurse. And then if you plug it into the divide and conquer recurrence, it gives you a linear time arc. Okay, this is a high level description of the median of the median point. So x, to find x is what you do all this, find the median of median, divide it into blocks of size 5, find the median of each block, and then find the median of medians, and that is your x. And the property of x is that some good fraction of elements get thrown out here. So regardless of where you recurse, your size of the array you recurse is smaller. So you plug it into your divide and conquer recurrence, it gives you a linear time. Okay, this is something you are supposed to have seen in your algorithms course. Now let's see how I would implement it in our read-only memory model. What are the limitations? What is the problem, right? Suppose I find the approximate median somehow. The problem is that this algorithm would compare and move all elements smaller than that to one portion and then recurse. But we are not allowed to move here. We don't have a lot of space to even copy all these elements. Okay, so that's one challenge. So one way we could handle is, so that means your array is not moved at all. You can't move interesting elements to one portion. So suppose this is my array and I've done my x and I found all those less than, greater than. So, and suppose I can mark which of these elements are some interesting elements to the left where I want to recurse. That's one way to remember, and that's like order n bits. Okay, I don't have space for that. So here is a solution which Munro and Patterson came up with. It's very nice, and what they said is the following. Okay, so let's say your recursion somehow says that you have to recurse in this portion. So what I will do is simply remember x, that's all. Constant space. Okay, and then when I am doing my recursion step, I only look at elements whose value is smaller than x. Okay, this is very similar to how do I, our sorting algorithm where we repeatedly find the minimum, but I remembered something and say among all those elements which are larger than this, I will find the minimum. Okay, so somehow this guy is acting like a filter. It tells you that if you find somebody smaller than this element, ignore it, move on. Only if it is larger, remember and find the maximum or minimum among them. This is how we did the sorting algorithm. So very similar to that. Here, the algorithm is that if you have to recurse in this portion, just remember x and maybe the smallest out of this element, right? The small. Keep these two elements. They're called filters. So in my next pass of the median algorithm, I only care about all elements that fall in between these two elements and do whatever work I want to do. Okay, so this is constant space because I'm remembering only two elements. And eventually this filter narrows down. It becomes like one element and or maybe two elements, and then I'll find something smaller than in between this and I will output that. Okay, so that's again a high level description of my median algorithm. I haven't told you the details. How do I find x? How do I find x? How do I repeat and so on? But this idea of if I have to recurse in one portion, I'm just saying here is a clever way of remembering that with constant space. Is that clear? Put +1 if you understand, and -1 if you don't. No +1, no -1, it means what? We're all. You can put 0 if you don't care. Okay, good. I see a few +1s. No -1s. Okay, good. So let's move on. Maybe even if somebody is not very clear about what's going on, when I describe a little more details, you will understand what's going on. Okay. So what is our goal? Into the 1 plus epsilon. So let's even say I'm going to give you an n root n algorithm. Okay, remember, if you're talking about finding median, which can be done in linear time if you have no constraints, but beating n square is a challenge here. Okay, if I'm giving only constant space, and I'm going to tell you that actually you can do it in n root n. Okay. So here is again, thing we should have realized is that, okay, I'll describe some sort of an algorithm and then we will do. You should, the moment I get something like root n, you know what I might be doing, right? I'll divide my array into blocks of size root n. So right now everybody is a candidate. So my filter is the smallest and the largest of the list. All elements greater than or equal to this and less than or equal to this are candidates for the kth smallest I'm looking at. So what I'll do, I will find the median of this list in order n time. Can I do that? In this little portion of this little block, I want to find the median. Can I do that in linear time? And how do I do it?
N is root n squared, so.
Exactly, right? Quadratic algorithm, apply. We know with constant space, we know we have a quadratic algorithm to find the median. So n is root n square. So in order n time, I find the median. Good. So that's my sort of the approximate x I talked about earlier. That's all. That's sort of my first step. this first step, this step is essentially my order n time. I found that. So now I will compare everybody with X and find the rank of X in the entire list. Okay. So if I am looking for 30th element, kth smallest element, but if there are 15 elements less than X, then I know that I have to recurse on the right portion of this array. Otherwise, I have to recurse on the left portion of the array, depending on. So I can compare X with everybody. This is one round, one pass, constant space, and find its rank. And I am looking, okay, so let me also remember K. This is also the three things I remember, constant space. So now, depending on K and depending on this X and depending on the rank of X, I know I have to recurse on the left side or right side. So depending on that, I will update this by X or update this by X. So what do I mean by that? All I'm saying is anything smaller than X, I'm going to ignore because I know I am going to recurse on the right portion. Anything smaller than X, I'm going to ignore, or larger than X, I'm going to ignore here if I'm recursing on the left side portion. So I update this filter. That's it. Okay. And recurse, repeat, continue. So at a high level, again, I need to tell you details of what do I mean by repeat. A high level, what is it? In linear time, I am guaranteed to throw away at least root n over 2 elements. Agree? So let me write what I'm saying. So we have spent order n time because we found the median. Next step, at least square root of n over 2 elements eliminated from my contention. Is that clear? Can somebody tell me? Do we need to find rank from each block or entire array? No. So just in this first block, I'm not doing anything else. Just in this first block, I find the median, order n time. Then I find the rank of this X in the entire array. So I compare X with everybody and I figure out what is X's rank. So X's rank is maybe 53. So I am looking for the 31st element. So that 31st element is less than X. So I update this by X to say that, hey, now everybody less than X is what is something I should worry about. So to answer your question about, I find the rank of X in the entire array. So now I claim that regardless of whether you update this or this, it is regardless of which side you recurse, you are guaranteed to throw away root n over 2 elements. Do you agree?
Yeah, that's because the rank of the median is root n by 2, right?
Exactly.
So,
yeah. So there are, in this block alone, root n by 2 elements are to the left and root n by 2 elements are to the right in this block. When I compare it with others, there may be more elements that's thrown out, but I'm being very conservative and I'm saying at least, regardless of which side you recurse, root n over 2 elements are eliminated. Okay, yeah. I'm done more or less because what have I done? I spent linear time. I've used only constant space. I have thrown away root n over 2 elements. Another linear time, another root n elements will get deleted. Eventually, in n root n time, I'll be left with only one element, which is the median. Okay, there is one more detail need to be worried, but this is more or less a high level answer. How do I capture the elements which are eliminated? How do I know which elements are eliminated? Can somebody tell me that? Because I can't move elements. I don't know. I'm not throwing things out, but I know that I'm recursing on the left side or right side, so some elements are eliminated. At least this many elements are eliminated. How do I know that?
Using SM, smaller and large variables.
Exactly. This filter captures that. Exactly. This small and large value captures it because then I know that I need to care only about elements in this array which are in between this. When I scan through and I find somebody smaller than this, somebody larger than, I can ignore that. So all I care about is elements that are inside, in between them. And so this filter eventually becomes the range becomes smaller and smaller in about root n steps. Each step I'm spending linear time, I will get my median. Okay, so that's the high level description of my n root n algorithm. There's one little detail I need to worry about, which is that, remember I said I'm going to pick root n elements and find the median. But next step, many of these elements are not candidates at all. So how do I find the root n elements which are candidates? Okay, so that requires some work. Maybe I won't tell you, or I'll briefly tell you. Whoever catches it, fine. So here is my overall algorithm. Find the block that contains, now I'm calling it interesting elements, okay, which means these are candidate elements, not just the first two root n elements, because some of them may not be candidates. Initially, everybody is a candidate, but in the next step, some of them are not. So I'll find the two root n interesting elements and then find the median x of that block in order n time. Can I really find it in order n time? Because this block may be very large now, because there are lots of elements that got eliminated. So this is one little detail I need to worry about. But after that, compare all elements with x based on the frequencies, identify the portion to recurse, and update the filters. That's all the algorithm. About root n elements are eliminated at each step, and hence in each phase, order n time, overall n root n time. So only different issue to deal with in step one is interesting elements are not together, but there is a way around it. Okay, I'll put it here. So I'll just say it. Maybe I won't dwell on it and move on to the next thing I want to, because I'm sort of running out of time. So initially I picked the first root n element, which is fine. Eventually what I do is, suppose R is the number of elements remaining. I look at square root, a block that actually contains square root of R candidates. And I can argue that there will be a block of size n over square root of R, which is not very hard. Then apply my quadratic algorithm on this, pick that median as my approximate median, find its rank, update the filter, continue. So that's sort of that. Now, how do I improve it to n to the 1 plus epsilon? Well, instead of picking root, why did I pick root n elements in the first step? Because at that time I only quadratic algorithm. But now I have an n root n algorithm, so I can pick some larger size block, something of size n to the 2/3, and apply my quadratic algorithm and still remain linear. And I continue, so I end up throwing a lot more elements at every step, and the number of passes comes down, and I can improve it. Okay, I won't say much more than this because it's just a little technical step, but I've given you an overall idea about how this algorithm works. Okay. So this can be generalized to n to the 1 plus epsilon for any constant epsilon, and the epsilon can be pushed up to certain function of n as well. There have been some improvement to these algorithms, so maybe I'll skip all this. Okay. So this is a some interesting open problems on what is the best in terms of with log n space. What is the best running time you can get? Even with constant space, what is the best you can do? These are not completely resolved yet, but this is some interesting direction. Okay, any questions or comments before I get to the last topic, which is breadth first search, something on graph algorithms. Give you a minute if anybody has any comments or questions to ask. So the overall theme is that your input is fixed, not allowed to be moved, and you have small space. What can you do? Okay. So we did sorting, we did finding the median. There's a whole rich literature on these topics. And the next thing I want to do, this is fairly recent work actually. Let's talk about graph algorithms. So yesterday I told about in-place graph algorithms where you allow movements of your adjacency list within the adjacency list, and you can do BFS and so on very efficiently. But now here I'm saying you are given an adjacency list. Okay. And so on. Let's recall how BFS works and how much space BFS actually needs, right? So what do you do? Breadth first search the graph and start with the vertex, keep exploring to its neighbors, continue, explore, and so on, right? So there is this color, you have gray or black or white, and then you maintain a queue, right? So quick revision of BFS, start from a vertex. So first color all vertices white, pick a white vertex, add all its neighbors into the queue and color it black. And any vertex which is into the queue gets a color gray. Pick the first vertex from the queue and repeat until the queue becomes empty, everybody has become black, and you've grown your exploration, and you got your breadth first tree, or you can output your vertices in breadth first ordering. And overall, in terms of space it takes, is this queue and this color array. So this color array, there are about order n bits. For every node, you remember one of these three values, so it's like n log 3. And then the queue can potentially be order n, and each queue value is a number. So that will be like order n log n bits. Okay, and we want to improve the space. Here there is, with constant space and all, there is no way. Nothing is known. Nothing is known, even sublinear bits. What I'm going to tell you is a way to improve the space to order n bits. Okay. Sublinear is very hard. We don't know how to do it. Okay, I'll tell you how to just do with order n bits. Since I'm allowing order n bits, I'm going to leave the color array as it is. We can optimize on the constant, but let me not bother about it. So this is fine. The issue is only about the queue. Okay. So one way to deal with the queue is, the queue is a set of elements, right? Set of vertices. So I could have a characteristic vector and say a bit for which vertices are in the queue, which are not. So that will be like an n bits. So it looks like we are done, right? We managed to do it in order n bits, because all I'm saying is your queue has some subset of vertices. That subset I will represent it by a characteristic vector, which element is in the queue, which element is not. That's only n bits. What's the problem now? Can somebody tell me what more we need? Or is it clear so far what I said? And now how do I run BFS? Or what have I lost by?
We are fixing the order of the queue, sir.
Excellent. I lost the order of the elements in the queue, which is very important, because the way BFS works is that I pick the first element from the queue, add all its neighbors, put it in the queue, and continue. So how do I know the first element of the queue? Because if you just represent by characteristic vector. Okay, good. So what am I going to do? Here are some observations. First of all, if you have not seen this, you should go verify. The queue contains vertices from only 2 levels. So if when you are growing this BFS, right, at any point of time, sort of these are the vertices in the queue. And these vertices are only from 2 levels of the BFS tree. And in terms of exploration, let's see how much the order is important. Because somebody told me that by using a characteristic vector, I lost the order. But really, is the order important and how much is it important? Can I not just pick any vertex from the queue and explore its neighbors?
So we can.
Yes? No?
Yes, sir, we can.
Okay. How many people agree, disagree with this?
Yes, sir, we can.
So we just have to make sure that the vertex that we are processing right now is of higher level.
Okay. So who is
We should
this
not
saying this? Maybe when somebody is speaking, if you can turn on the video, it will be very useful. Just so I know who is speaking, because this is one of the disadvantages of a virtual meeting. Right? Yes. So who said this? You can at least share your name.
Sorry, sir. I didn't listen properly. Sorry, sir. What did you say?
Turn on the video and say whoever is answering.
Sir, I was Sarupashri, sir. My name is Sarupashri.
Okay, Arupashri. Yeah. So what she is saying is that order doesn't matter in some sense, but it does matter. You have to make sure you grow vertices on the first level. See, there are two levels. You cannot explore a vertex from here because there may be a vertex whose neighbor is here, but this may be a neighbor for this vertex as well. If you explore it here, this vertex will go to the next level. So you have to explore this level first and then explore this level. Within this level, order doesn't matter. But it's very important that you explore levels of the first level before you explore the vertices from the next level. So that is important. So Q contains vertices from only two levels. We need to explore from first level in any order before exploring the second level. Now this suggests instead of one Q, I will have two Q. So level 1 and level 2. Okay, so I have two characteristic vectors. I find a vertex from here, put all its neighbors whose colors are gray into the level 2, find another vertex which is here and change it to 0, find another vertex which is here, all its neighbors, put them here and so on. So explore this first and explore this next. And this is possible. This is like an n bits. This is like an n bits. So you just remember these two levels plus your color. So overall with order n bits, you can do this. Okay. Now what happens to the time? Well, you need to find some vertex here which is there. So you need to sort of scan through this list to find a one here, which could be expensive, but there are ways to deal with it. So let me just summarize what I just said. Represent the two level vertices using 2n bits. And what do you need to support? You need to support insert, delete. That's not a problem because some vertex whose neighbors get inserted into the next level. In a characteristic vector, you can do it in constant time. But you also need to find, is my level 1 empty? Is there somebody there? So I'm going to call that operation is find any element in that set. I'm trying to represent two sets, find any, and this can be done. So there's a theorem, such a data structure to support these three operations, insert, delete, and find any, using n plus little of n bits. Little of n is asymptotically smaller, where all operations can be supported in order and time. As a result, BFS, you don't lose much on the time, order n plus n, using 2n plus little of n, not quite 2n, plus color array. Okay, so that's another n or 2n kind of bits. Overall, I've reduced from n log n to order n bits. And the space, this is all like the last 5 years work. Space has been improved. People are still working on it. Are there any questions? Let's one if everything is okay. Otherwise, ask questions. Okay, good. Thank you. So Let me just briefly tell you what is known about depth first search. It's a lot more complicated. There's a whole lot of work. Again, it's your CLR's book, classical stack-based algorithm, takes n log n bits because again it remembers the stack, but it can be improved. The whole work started in 2014, and it's going on. It's going on in trying to reduce the space and trying to improve the runtime as well. You can do other applications of DFS, BFS, by connectivity, chain decomposition using order n bits. So sublinear bits, nothing is known. If you see this, it's just order n. Same with BFS. Whereas for sorting and selection, you can do it with constant space, even though the time short up. But for BFS or DFS, even with polynomial time, you don't know, you can do it in even sublinear space. Okay, so that's sort of the summary of what I wanted to say. What we did was that we assumed that my input array is in a read-only input array or a graph or whatever, and we're allowed some small space, and we're trying to rework some of the algorithms we have learned in my algorithms course with our hands tied, with small space. And some of the tools are all this about this blocking and this filtering and remembering small things to capture what we have done so far, or some of the tools we did. Okay, let's stop here. Are there any questions, comments? Otherwise, we will continue at 12:15. Saket?
Yes, we'll continue at 12:15.
Yes, and Saket will continue on some approximation algorithms with our hands tied, like with read-only memory and small space.
So see you all in 10 minutes.
Okay.
Hello, am I audible? Okay, great. So okay, so let's start. Okay, so okay. So before we start, let me let me run a poll, okay, and just put yes and no in the poll. That will give me some idea about how to go about today's lecture. So I'll give you 30 more seconds. Please vote, because that is what will decide how I go about teaching you today. Thank you. And look, anyway, it is anonymous, so it's not that I'm going to know. This is like Indian election, you know, like just 70% people votes. Okay. Okay, so 14 seconds to go. Please vote, please vote. There are 12 people who didn't vote. This much I know. So that also shows that maybe those 12 people are just online and they're away. Okay. Very nice. Okay, so I think, okay, so there's still 12 people not voted. Okay, guys, I'm going to end the poll now. Okay, if you don't want to participate, not much I can do. Okay, so I end the poll. Yeah. Okay. Do you see the result on your shared results? Do you see? Yes, great. So 31 of you tell me that you do know about NP completeness. And 9, no. Approximation algorithm, even less. 16 of you say yes. 24 you say no. And vertex covered problem, 24/16. Okay. Okay. Great. I will not ask you how many of you know what you call polynomial time algorithm. Okay. This question I wouldn't ask you. Even if you don't know, I will going to assume that you know. Okay. Okay. Good. So let's start trying to build over this, and then we'll get to the space constraints as we go forward. Okay. Okay. So for this talk or lecture, NP completeness is going to be just the following line. Okay. This is not how NP completeness is defined. Okay. But this is just something you can keep in mind, and this is good enough for this purpose. Okay. Okay. So a problem pi, like if a problem pi is NP complete, okay, then there does not exist any algorithm, okay, that solves all instances optimally in polynomial time. Okay.
Yeah. நான் பாத்துக்கிறேன்.
Why don't you people just mute yourself if you are not asking question? Okay. Shruti, can you mute yourself? I can mute you. Great. Okay. Yeah. Okay. So let's look at what I'm saying to you, that if a problem pi is NP complete, then there doesn't exist any algorithm that solve all instances optimally in polynomial time. This is not the definition, but this is just something which will be just enough for our purpose today. Okay. So it just means that, so for example, you just now saw about breadth first search, depth first search, or any other such problems. So what are the instances of this problem is a graph, right? And breadth first search, depth first search runs in polynomial time, right? And gives you breadth first search or depth first search, what is that called? On all instances, right? Or I don't think this is much, this is not very good example. I think the better example will be, say, shortest path or maximum matching. Okay. So what is an input of shortest path? So there could be all pair shortest path, or so input is G, a pair of vertex S and T. And what do I need to output? A shortest path between S and T. Here, input is G, and what do I want to output? A maximum sized matching. How many of you know matching? If you know matching, put +1. Okay, maybe I should put, is there anyone who doesn't know matching? Please put -1. Okay. Oh, there are enough you don't know. Fine. Shortest path, if someone does not know shortest path, please put -1. Okay, fine. So I assume that everybody knows shortest path, but many of you do not know maximum matching. So given a graph G, okay? Matching M is a subset of edges, and it has a following property, right? So for any two edges, E1, E2, which are element of M, okay? E1 and E2 do not share any endpoints. For example, suppose I have following graph, okay? This edge and this edge is a matching edge, because if I look at this edge and this edge, they do not have any vertex which are in common, okay? So this is a matching. And when I say maximum matching, I want to find subset of edges which pairwise do not share any endpoint and edge of the maximum side, edge of the maximum cardinality, okay? So for example, this red edge and this brown edge are not matching because they have a endpoint in common, okay? But is the two red edges maximum matching in this graph? I don't think so, because we could have taken this edge, and this red edge. This is a maximum matching because look, every endpoint can only participate in one of the edges, and we have a matching, or we have a set of edges where every vertex participates into this. So we cannot form much more than this. Okay, so hello, right? So can you tell me if we have a graph G on n vertices, a maximum matching can have size n square? Is it possible that a maximum matching in a graph can have size n square? Very good. N? Okay, good. So Agatsya tells that it is at most n by 2. Can you unmute yourself and explain to people why it is at most n over 2?
Yeah, so we are basically forming pairs of vertices. So in that case, there can be at most n by 2 pairs, right? N by 2 pairs which are edge disjoint. Yeah.
Which are pairwise vertex disjoint, you mean? Am I right?
Yeah, sorry, yeah.
Okay, great. So now is everybody clear with matching? If not, then put minus. Oh, sorry. So now we have these two problems, shortest path and maximum matching, right? Now we know what these problems are. These problems are polytime solvable. Okay, both, which means that if I give you any instance of this problem in polynomial time, you can find an output or you can find an answer to these questions. Okay, but if a problem is NP hard, we cannot design an algorithm for that problem, which for every instance, there may be some instance on which we might be able to find a polynomial time algorithm, but on every instance, it is not possible to find a polytime algorithm. Okay, so this is all that I want to tell you about NP hard problem or NP complete problem. Okay, so now clearly I cannot have an algorithm A, right? That solves all instances optimally in polynomial time. So suppose I still want to design an algorithm which works for all instances, runs in polynomial time, then what do I expect from such an algorithm? You get my point, right? Then we relax the condition of optimality, okay? And we say, look, I'm fine with an approximation. And what I mean by I'm fine with an approximation, look at this maximum matching problem. Hey, maybe there is a maximum matching of size n by 2, right? But I can find you a maximum matching of size n by 4. This is all that I can guarantee, for example. But maximum matching is not a good example because it's a polytime solvable. We can always find a maximum size matching. But just to put my point across, approximation algorithm will mean, okay? So what is an approximation algorithm will mean? So an approximation algorithm will mean, right? As I told you, this is an algorithm A, okay? And it is guaranteed, it is, here's a box, this is an algorithm. It takes an input, some input, okay? This box runs in polynomial in time and outputs a solution, okay? It outputs a solution. Now, but it outputs a solution that may not be optimum, okay? So for example, if I was asking for a shortest path problem, suppose I wanted to derive I wanted to derive a factor 2 approximation for shortest path problem, right? Then what will this algorithm do? Okay, so I know that it takes an input s comma t and g, and it needs to output me a path, okay? Then I will say, oh, look, the path which the algorithm is going to return, okay, the path is no worse than twice of the best solution. Meaning, okay, meaning suppose the length of the shortest path between S and T in G is say L, then our algorithm will return a path P star such that length of P star is guaranteed to be at most 2 times L, right? So look, I'm not telling you that I will give you the best solution, but I will guarantee you that I will give you a solution which is not worse than factor 2 with respect to the best solution, okay? So this is what is the notion of approximation means. So there was nothing about 2. I could have taken any C and then a factor C approximation will mean returning a solution of size at most C times optimum. Okay? Okay? So is the idea clear? Right? But this is with respect to minimization problem, right? Right? So where we would like to get how does this approximation algorithm scale to large graphs with larger path? It has nothing to do with the graph. So if look at any graph and look at ST, whatever is the length of path there, it is not going to return you a path which is more than twice in that particular ST. So for every instance G comma, so think of this way. So what is guaranteed? So let's write opt G comma S comma T, length of the shortest path between, okay, S and T in G, okay. Okay, and now let's call LGST length of the path returned by algorithm on GST. So what are you guaranteed is that, okay, so what I'm guaranteed is that alg GST divided by optimum GST is at most 2, right? Okay, and if we had factor C approximation, then this 2 will be upper bounded by C, right? So this is the point, right? For every instance, I'm going to return solution which is not worse than C times the best solution in that particular instance. Okay? Okay. Okay. So this is how the notion of notion of approximation is defined for minimization problem, right? But how should you define the notion of approximation for say C equal to 2 for maximization problem, right? Say C equal to 2, but for maximization problem. Example, maximum matching, right? Right? So here also, so suppose what will be opt of G, let it denote the size of a maximum matching of G, okay? And let's say alg G is size of the maximum matching returned by algorithm when run on G. Okay, so now there are several ways, right? I can say that, look, either I could define that, look at the opt of G and look at the divided by alg of G. This factor is at least C. If I'm going to assume the C is greater than or equal to 1, right? You get my point? So what does it mean? That, look, I'm not too much away. So if C would have been 2, what is the meaning of this? That, look, the solution which is returned by algorithm, right, is at least half better. Or in other way, if you want to see much more, so probably you could also use this, but it's up to you, how do you want. But then this will be like how much fraction. So then C will be less than or equal to 1, right? So for example, I say, hey, it is at least 0.5 approximation, meaning whatever solution alg returns is at least half times the optimum, right? So maybe this is a bit more clearer for the approximation algorithm. So for maximization problem, so when I say, hey, max matching has 1/3 approximation, meaning this constant is at least 1/3, meaning the solution which I'm going to return is at least 1/3 times optimum of the best solution in that particular instance. But a lot of people use either this or either this, depending on their context or depending on their notation, okay? So is the notion of approximation algorithm clear to you? Is the notion of NP completeness clear to you? If yes, put +1. If it is not clear, put -1. Okay, good. So, so let's change our track and let's make a couple of approximation algorithm. Okay, just to get used to this notion, and we will also use this throughout this course. Okay. Okay. How many of you know how to find a maximum matching in a graph? Or how many of you don't know? If you don't know how to compute a maximum matching in a graph, put -1. Okay, excellent. Fine. Very nice. Okay, good. So, okay, I'm not going to teach you how to compute and how to compute a maximum matching of a graph, but I'm going to teach you how to compute a factor half approximation or factor 2, or so let's go with factor 2. A factor 2 approximation for maximum matching, right? So my convention is alg. No, my convention will be opt by alg. Okay, my convention for maximization problem will be opt of G divided by alg of G. Okay, this is my convention, just so that we know what I mean when I say factor 2 approximation. Okay. So say this is an algorithm to compute, say, maximum matching. So input, it takes G and it is going to output a matching M of G. Okay. Can anyone tell me some algorithm for matching that you can come up with? Forget about maximum or this, like some heuristic that you can think of algorithm for matching. Any heuristic. Anybody else? Shravan, can you substantiate or pick edges randomly?
Sir, so like we just don't want the edges to share a common vertex. So like say I pick what edge, all the edges from the level 1 of my BFS, leave the level 2 and pick level 3 edges, and like yeah, that need not be
But
the
in
maximum.
level one, look. So what do you mean? Graph induced on level 1 vertices?
Yes, sir.
Okay. So if I look at a graph like edges with both endpoints in the level 1, how will I find a matching there? Or there you are just going to pick one edge?
No, I meant from the source to level 1, not within level 1.
Okay, source to level 1, I found how many of them?
Let's pick all.
How can you pick all? So I have a source.
Oh, no, we can't. Yeah, we just need to pick one. Yes.
No, we are not assuming that's input is bipartite graph. Sanjay?
Sir, actually, I'm not sure about random, but pick one edge, leave the ones in neighbors of them, and then pick the next edge and keep moving forward.
Okay.
That is find a maximal matching.
So how many of you heard of this word called maximal matching? So, okay, so let me follow what he said. So here's an algorithm. Okay, here's an algorithm. While there is an edge in G, okay, do whatever you're going to do. So initially, I'm going to set M equal to empty set. Okay, and I'm just going to follow. Okay, pick an edge in G. Okay, any edge in G. Okay, pick an edge E in G. Add E to M, and then G equal to G minus U comma V, where E equal to U comma V. Okay, that's it. This is my algorithm. Okay, so as all of you have pointed out correctly, this is greedy basically. Okay, okay. So two questions, or rather three questions. Question number one, is M a matching? Question number two, does this procedure run in polynomial time? Question number three, what is the relation between optimum of G and M? Okay, so first of all, which of these question is easy?
The first one.
Okay, why first?
While we pick an edge, we should ensure that it does not have any common endpoints with existing edges in M.
Okay,
Else it
have
won't
we
be a
ensured
matching.
that?
No, so this is not a matching, right?
Okay, why have we not ensured that?
No, we have ensured that.
Because let's say that we have two edges with a common vertex. In the first iteration, we pick one edge. The second iteration, we can pick the next edge, and that is not a matching.
Can you read the algorithm?
We delete both the endpoints of the edges from the vertex set.
Yeah.
If I pick
we
UV,
remove the vertex.
then G is assigned
I'm
G
sorry,
minus
I thought
UV.
we removed the edge. Oh, I'm sorry, I didn't follow that. Yeah.
Okay, maybe I should. Maybe I didn't write it correctly. Okay, UV. Say edges we are going to write. So I'm going to delete this. So does everybody is clear that this is definitely a matching? Okay. Does this procedure run in polynomial time?
Yes.
Yes, very good. I mean, if you don't tell -1 or no, I'm going to assume that all of you know. This is fine. Okay. Okay. And what is the relation between opt G? So suppose, so what I mean by this, suppose M star is a maximum matching, right, of G. Okay. And M is the maximum matching, is the matching, not maximum matching, is the matching that is returned by our algorithm. Okay. Okay. What can we say? What is the relation between M star, and M, right? Well, okay. So ideally, I would like to show that, look, cardinality of M is at least M star divided by 2. Suppose if I show this, then have I shown that, then I have shown that my algorithm has a factor 2?
Yes.
There is a question, is there a similar relationship with the weights of the graph? Meaning, there's no weights. Arjun, can you explain yourself what question you have? Okay. Okay. Anyway, so how do we go about showing this? So this is very simple. Okay. Okay. So suppose this is my edges of M star. This is my edges of M star. And now I want to write down, I pick up. So suppose M is E1, E2, dot, dot, EL. Okay. I look at edge E1. Okay. Now, if I pick up an edge E1 and I want to see if I pick E1, how many edges of M star I cannot pick? Tell me. So suppose if I picked up E1 in M, how many edges in M star I may not be able to pick? Like, how many edges of M star can I knock off? Suppose E1 is some UV, right? So there are two things can happen. E1 might also be present in M star, okay? So E1 could be present in M star. Then this edge knocks off only one edge of M star, and there are still so many edges which are picked. But what could happen that, look, E1 is only UV, so maybe there is an edge with U, and there is some other edge with V, with maybe some other partner, say U prime, and some other partner with V prime. So the moment I select U1, I cannot pick up this edge U, I cannot pick up this edge V prime. Am I right? So every edge I pick in M, I can only knock at most 2 edges of M star, right? Which implies, what does this implies? This implies that the number L is at least, suppose this is Q over 2, right? You get my point? So for every edge here, you pair up whichever, so I take this edge and I pair up which edges it will knock off. So now this pairing only has, this pairing has size at most 2, okay, right? Which implies that the edges, the matching which our algorithm has considered, okay, is of size at least M star by 2, okay? Now you can ask, well, is it possible that an edge doesn't knock off anything? It is possible that, hey, why it will not, some edge EL does not knock off anything, which implies that look up some edge. Look up why, like, so I look at E1, E2, EL, and I delete all the edges which they knock off. Is it possible that some edge here remains? Is it possible that some edge remains here?
No, because if that would have been the case, our greedy algorithm would have picked this edge.
Exactly, because the moment, what is our algorithm doing? In some order, it is deleting the endpoints of these edges, right? And when is it stopping? While there is an edge in G, you do something. So if some edge here does not, if there is an edge which remains after this pairing of this business, it implies that after I deleted all these vertices, my graph was not empty, right? So every edge here either knocks off one edge or 2 edge, right? And hence L is at least Q over 2, okay? So now we are happy, right? So I look at all the edges and I can pair them up. So all these edges of M star can be either paired with, it can be paired with one of these edges, and the set which is with respect to some edge is of size at most 2. So that implies that the number of objects that you need to knock off everything here is at least Q over 2, right? which implies to us that cardinality of M is at least M star by 2. And though many of you do not know, maximum matching algorithm, now we know a factor 2 approximation. Am I right? Okay. Okay. Until any question, I will move to the next problem. Okay. Okay. So if there is no question, okay. So let's get to the problem of vertex cover. Okay. So there are several versions of this problem. Okay. So let me write a decision version. Okay. So what is the decision version problem? So you're given an input G, K, and objective is, does there exist a set F subset of vertex set of G of size at most K such that every edge UV has at least one endpoint in S. That is either U is in F or V is in S. Okay. It could be that both are there in this. Okay. Okay. So this is called a vertex cover problem. So for example, if I look and I ask, is there a vertex cover of size 1 here? Answer is no, because if I pick this edge will not be picked. If I pick this vertex, this edge will not be picked. If I pick this edge, this vertex will not be picked. But does it have a vertex cover of size 2? Yes, because I can pick any two vertices, and then all the edges have the property that there is at least one endpoint contained here. Or in other words, the property is that if you look at G minus S, there is no edge. Okay? There is in G minus S, there is no edge, because what is the property of S? Every edge has at least one endpoint contained inside S. So if I delete S, I shouldn't be finding any edge, right? Because if there would have been edge completely disjoint from S, then S is not a vertex cover. Okay? So this is the decision version. And the other version which we will be interested in is optimization version. Okay? Where input is G, no K, okay? And objective or output is find or output minimum sized vertex cover of G, right? I want to output an S which is of the smallest cardinality. Okay. So unlike matching, decision version of vertex cover is NP complete, and optimization version is NP hard. Okay, so there cannot exist a polynomial time algorithm for this problem, but it's a good exercise to check that vertex cover is in P on bipartite graphs. Okay, but so can you suggest An approximation algorithm for vertex covered? Some algorithm, okay? The way we did it for matching, okay? So I want to make an algorithm for vertex cover. Can you suggest an algorithm? Any algorithm?
Yeah, it's similar to the matching algorithm. Just if you just add an edge to your answer, and then remove all other edges from those two vertices from your possible answer, future possible answer. Yeah.
Okay, so there are lots of possible answers, right? So
yeah, just randomly pick an edge, and then yeah, you're not allowed to pick any other. You basically delete the two vertices from the graph.
okay, so you are basically telling me to do the following thing.
Yeah, I have a question. So why will we pick edges? We will pick vertices, right? It's vertex cover.
Yeah, so ask him, no? I was not saying
Yeah.
anything. Okay, all he said to me is that, okay, I told him to output a vertex cover of G. Okay, and what he says, let me repeat. He says, okay, you call your M S. So I take M equal to S. Pick an edge in the edge. Now, rather than saying add E to M, he's saying add, suppose, pick an edge E equal to UV in G, and correct me if I'm saying add S union U comma V. Okay, okay, this is all that you are saying. Am I right?
Yeah, I think so. Yeah.
Okay. Okay,
So
very
we
nice.
can also delete all the neighbors of U and V. No? So like,
That is anyway is covered, no? G into G minus U comma V. No?
okay.
If I put UV, then I deleted G minus U comma V.
Okay.
Okay. There were also some other suggestion by pick a vertex, okay, that covers most number of edges, delete this vertex and repeat. Okay. So let me focus on this algorithm because of the lack of time. Is that first of all, clearly this algorithm runs in polynomial time, but why is S a vertex cover? Is that clear to you? Is S a vertex cover which is constructed by this algorithm? Look, this algorithm does the following. At any point of time in the graph, it picks an edge UV, any edge, adds U and V to S, deletes U and V, and recurses. Right? This is all that this algorithm does, right? So look at your S, right? And so I claim that this is a vertex cover. Why? First of all, what am I doing in a process? All the time, I only delete edges which for the vertices which I put inside. Okay, so it is not possible for. But now, when do I stop? When there is no edge in the graph, then I stop. Okay, when there is no edge in the graph, then I stop. So which implies that, look, if there would have been an edge which is not covered by S at all, then that edge here will appear here, and then we would have picked that edge. So G minus S is not empty graph, right? So because we are only stopping when there's an empty graph, which means that if I delete S, right? So look at the last time when S stops, right? Look at G minus S. Okay, so how we have picked up this, right? So we have a current G, it has no edge. It means the vertices of S does not cover this edge. Okay, so it is indeed a vertex cover. Okay, but what else are you guaranteed? So let me maintain two things, okay? I also maintain M, okay? And what I'm going to do, I'm also saying, okay, add M to U comma V, this edge U comma V. Right? So I can also rewrite this algorithm as follows. Compute a maximal matching. Okay? Compute a maximal matching. Okay? And then my question will be, if I computed a maximal matching, okay, take both its endpoints. Endpoints, right? As vertex cover. This is my claim. Right? So why is this a vertex cover? Because what happens here is your maximal matching. And what you did is basically you took the endpoints of this. Okay. Now look at any edge. Okay. Right. So if there would have been an edge here, not incident to this blue vertices, it means the red colored form, it does not form a matching, maximal matching. I would have added to my matching set, right? So if I take a maximal matching, take both its endpoints, then it does forms a vertex cover. What is its approximation? Well, let's try to understand. This is very simple. Look at any vertex cover, any vertex cover. If he needs to cover this edge, am I right? Right? He needs to cover this edge. He needs to cover this edge. He needs to cover this edge. And what did I do? Well, look at a vertex which covers this edge cannot cover any other edge, right? Because a vertex which covers this edge and this edge, like either this vertex can cover this edge or this vertex can cover this edge. But whichever it may be, those two vertices cannot cover any of these edges, which implies that any vertex cover must pick at least one endpoint from maximal matching edges, which implies that any vertex cover had size at least greater than or equal to m, right? And what we have done, we have found an S of size at most 2 times m. Why? Because we found a maximal matching and took the both endpoints of this maximal matching. Okay? Okay. So that implies that the algorithm we saw has factor 2 approximation. Any question? If you have any, if any of you did not understand it, please put -1. Okay. Well, all and good. Now, the question which I would like to address here is can we implement these algorithms when we only have order log n extra bits of auxiliary space? Okay, so is the question clear to you? So look, I told you 2 algorithms. I would like to implement these algorithms, okay, when you have only read-only memory, you have a write tape, which you cannot access, and you have small work tape. So this read-only memory, you can read as much time as you wish, but you can only keep in this work tape, you only have small amount of space to this work tape, and you can write in a separate tape, whatever solution comes, but you cannot, whatever you write here, you cannot read it. It is lost. I mean, okay. So now notice that in both the algorithms, we need to maintain a maximal matching, right? We need to keep a set S or we need to keep a M, right? So to keep that set S or M, the space here is how much? How much space will these two algorithms will take? Anybody? No, space is just the size of the maximum matching, right? Maximal matching. So which is like order n. Okay. Okay. But now, suppose I told you that this work tape has root n space. Forget about, or let's say n divided by log square n space. Okay. What kind of approximation algorithm can be derived for just these two basic problems like maximal matching and minimum vertex cover, right? These are very simple factor two approximation. All of you are able to design. But now when I tie your hands, can we still design good approximation algorithm? Right? Now we will forget about time, running time. I can give you time as much as you want. Okay? But the auxiliary space that you're allowed to use is no more order n that you have used for last two algorithms. But look, root n space looks very hard. And if I tie your hands and say, look, I'm only allowing you polylog in space. And when I say polylog in space, you can think of polylog in words or polylog in bits as you wish, right? What can you do? Okay, so I hope this motivates you to this set of questions. And tomorrow at 10 o'clock, we will look into these questions and we'll carry on from there and then move to the difficulties one faces when you are designing these kind of algorithms to designing streaming kind of algorithms. And you will see streaming will be introduced to you, I think, in the last lecture today, I guess. Okay. Okay. Until unless there is no question, we will continue tomorrow starting from here at 11. Sorry, not 10, but 11. Anybody has any questions? In my opinion, this is the right place to stop. That we have seen the algorithms for two basic problems. I would like you to go look into this, check it out, do as much as you can, and try to see for these two basic problems, what can you do if your hands are tied? Think about it, and then you will be able to appreciate these algorithms much, much more. Venkatesh, would you like to add any comments?
No. Fine. Yeah, thanks.
Okay. And today we will have a tutorial at 4 o'clock. Okay. And there we will look at this, apart from everything else, we will also look at this heuristic which Agastya proposed, pick a vertex which covers the most uncovered edges and repeat. What happens? Like what kind of approximation does it give? Apart from also looking at all the other things which is there in your sheet. Okay. Okay. So if there is no further question, then let me say thank you. Bye-bye. Okay.
So next session starts at 2:30, right?
Perfectly correct.
Okay. Thank you, sir.
Okay. Bye-bye.
Hi, am I audible?
Yes, sir.
Okay. Let us wait for a couple of minutes if somebody wants to join. Okay, let us start. It's 2:35 now. Like yesterday, we will follow the same strategy. If you didn't understood some of the things which I mentioned or explained, please write -1 in the comment, and then I will explain it again. And you are feel free to, unmute and ask questions. And today I will talk about streaming algorithms, and we will see like some of the algorithm in the yesterday we have seen it can be made into a streaming algorithm, and then we move on to graph streaming algorithm and see some examples there. So what is this model of computation? Okay, so imagine that you have like a huge data which is as a sequence of tokens. Okay, and for the time being, assume that these tokens are numbers, right? Say E1 is a number like 1 or 2, 3 or 1,000, something like that, and the E2 is another number like that. Okay, and this sequence is so huge that you cannot actually fit all of this data in your main memory or like a RAM. Okay, then you are forced to work with limited memory, right? So so you will have a memory whose size is B, which is much smaller than the all input sequence, which is E1 to EM. Okay, and so what you could do is like you can think that these tokens are coming like a stream. Okay, so first you see E1, E2, E3, and you have only a limited memory that is B, which is much smaller than M. So you cannot store all of these E1, E2, etc. up to EM. But at the end of the stream, you have to compute some interesting functions of the input. So another way of looking at it is like there is just an input stream, which is E1, E2, etc. up to EM. And your algorithm can have a memory, which is B, which is much smaller than it. And you will be reading the input from left to right, like one by one. And you don't have, say, random access on this input. You can you can pass the input from left to right. This is another way of looking at. And then after you do one pass, and you will be able to store some information based on what you have seen in the stream in this small memory B, and at the end of the stream you should be able to output some questions related to the stream. And you can also think that instead of going only once, you may do it 2 or 3 times. Okay, so if you do it only once, then that is called one pass streaming algorithm. And if you read this input twice or thrice, then it is called 2 pass or 3 pass, like that. Okay, if you do a P passes on the input from left to right, then it is called a P pass streaming algorithm. Okay, and now examples of these tokens, you can think that this token is a number in some cases, and another case you could think that it is IP addresses which passes through some network switches. And in the case of graph algorithm, like that we will see, like we will think that as a edges, and in the case of matrix problems it is a row or column. So the input is listed as a sequence, and where the input could be any of those. Each of these token could be any of the listed things, or maybe something else also, right? And we at the end of the stream, we should be able to compute some question regarding the stream. Okay? Now, why it is important? Okay, as I mentioned, like while explaining the streaming algorithm, suppose the data is too big that you cannot fit into your main memory, And then what you need to do, you need to read it from, the secondary memory. And then again, you need to, just store back that on the secondary memory, like some portion of it. And the second block, you have to read it again, and third block, and like that, okay? So because of that, you will not get random access to the input, that is E1 to EM. So you need to do it, in a sequential way from left to right, okay? So if data is too big and your memory size is less, then you have to design a streaming algorithm, okay? Another scenario is like, the device itself is very limited. Suppose it is a network switch or sensor or something like that. Then its memory itself is too tiny. Like in a network switch, there will be like, millions of packets will be passing through it. And you cannot store information regarding all of those packets within that network switch, okay? So it is a limited space device, okay? Then if you want to compute some information, like, to which destination so many packets are moved or something like that. And again, another setting is like distributed computing, where like the data is so huge and you have a lot of machines, they are like distributed, and these machines will be computing, on some of the data which it has seen. Then it need to send some amount of data from one machine to another, and the costly thing is actually the communication between the machines. Then you need to work with, limited memory, okay? So these are some examples where like streaming algorithm is important, okay? Now consider the last problem which I have explained in yesterday, okay, which is the heavy hitters problem, okay? And what is that? So we are given an array of m elements, m integers, and we want to output all the elements, or all the elements in the array whose frequency is at least m by k. There will be at most k such elements, and we have discussed an algorithm that works, like this. So we will be keeping, k counters, that is d1 to dk, and these counters are associated with, some k elements in the array, and which is the potential candidate, that is s of 1, 2, 3 up to k. And then what we did is like we had a for loop that goes from 1 to m, 1 to m, and then we are going to base, like in each of the iteration, by looking at the value a of j and looking at the counters d and this array s, we will be modifying d or s, okay? And keep doing it, like, till like you do it in like one iteration, another iteration, like that, m iteration, one per the location of an array, like array element, okay? And at the end, what you do is you verify whether something stored in S is indeed a heavy hitter, okay? Now this you can think as a streaming algorithm that is doing, a two-pass streaming algorithm. So you have this array, and that the first element, this you can think it as a stream, A1, A2, A3, etc. up to AM. This is your stream, okay? And what is the first for loop doing? Like you are going to pass the input from left to right once, right? So you did one parsing, okay? And what is the memory you use? This two. And how much is that memory? Like 2k registers or 2k words. And so how much you will be storing? 2k log m, assuming the integers are within the range, within 1 to m, okay? So you will be using, space is this much, and within one pass, you will be making this array d and s, and for verifying that you do in the second pass, you again go through this stream, which is from left to right. That is, you go through that array from left to right, and then use the same array D to count and test whether an element stored in S is indeed a heavy hitter. And if that is the case, you will output that element. And so at most k elements you will be outputting. And yesterday we have proved that the algorithm is correct. Okay, and so you are doing two passes from left to right on the input array. So if you think that numbers on the array as the stream A1 to A1, then your algorithm is actually a streaming algorithm that does two passes. One is here and one is here. So what you have seen yesterday can be thought of as a streaming algorithm that that uses two passes, and the space complexity is this much. Notice that this is much smaller than m. Say suppose k is a constant 5, and this is 5 log m bits, and that is much smaller than m, exponentially smaller than m. Okay, so this is an introduction to streaming. Okay, so now I hope you understood the concept of streaming algorithm. So you need to compute something using small memory than the input, and you don't have random access to the input. You have to do the parsing from left to right, and if you do it only once, then that is the best. Then it is one pass streaming algorithm. If you do that parsing is twice, then it is two pass and something like that. Okay. And in the case of network switches and all, you need one pass because the data is not with you, it just passes away. But in the case of something stored on the secondary memory, then you could do two pass or three pass, but it is costly. Okay, now we move on to graph streaming. Okay, now, so what is a graph problem typically? Like a graph problem, like a graph is given. So a graph is given means its vertices is given. Its vertices is given. Also its edges are also given, right? And so it is given in some form, right? Like either adjacency list or adjacency matrix. And in the normal algorithm, you need to solve something related to that graph. For example, a graph is given, you need to find out a spanning tree of the graph. Or like, you need to test whether S is, like also you are given two vertices, S and T, you need to compute whether S is reachable from T. Okay. Now, how do we define graphs as a tree? So the way it is defined is as follows. Okay, I will always assume that the vertex set is labeled 1, 2, 3 up to n. This is the vertex set of the graph, and before the stream starts, we know this set 1, 2, 3 up to n. The only thing we don't know is the edges, like which are the edges between the vertices. This we don't know. Okay, the edges we don't know, but vertex set we know, and each vertex is labeled a number between 1 and n, and we know n. Okay, so this we know. Okay, but edges we don't know, and edges comes as a stream, like it is a sequence e1, e2, etc. up to em, seen as a stream. N is known, but m is not known. M will be known only after the stream ends. Okay? So this is the setting for the graph streaming algorithm, Okay. Now, why we should study about graph streaming? So if you look at the friendship graph of Facebook or Twitter, there will be like millions of people, and the edges represent if X is friend with Y, then there is an edge between X and Y. Okay. Say, X is following Y, then you add an edge between X and Y. Or like you can make it directed who follows whom. Okay. But look at that graph is huge. So probably you may not be able to solve something on such graphs using your your classical algorithm where you need all the input to be in your memory. Okay, so in that case, so suppose we know like there are only million people, there are million people and we know these people, and then like the edges is coming in a stream, and then we want to compute interesting questions about the graph. Okay, now the question is like the important limitation here is like we are allowed to use only limited space. What is limited space? The space should be much smaller than this, should be much smaller than m. Okay, now look at the last example we have seen. Say suppose I want to compute heavy hitters where k equal to 5. What is the space complexity used there? What is the space complexity for the heavy hitters? A 2-pass framing algorithm. Like just
Big of
couple
K
of
log M.
yeah,
K log M.
big of K log M, right? So I think about K being a constant. So ideally we could think that, okay, I need something whose like space is like a log M, like order log M, and here M is the number of edges. Okay, so ideally we could think that, but unfortunately, like, so what could be the value of M? M can be at most n square, assuming there is no parallel edges or loops like that. Okay, it's a simple graph. Then M is at most n square. Okay, and log M is actually order log n. Okay, so ideally we could think that, okay, it will be great if we could solve problems using this much space. But the sad news is, for many of the graph problem, one can prove that, if you are going for say 1-pass streaming algorithm, then we need, at least omega n space. Okay, and for many problems, we also know that if we go for p-pass streaming algorithm, we need space something like n by p. So essentially, like it says that getting order log n is very difficult, like impossible, like because there is a lower bound. Okay, if you want a streaming algorithm that works for certain problem, you need to use at least n bits of space. Okay, and such lower bounds are proved. Okay, and we will see like in this workshop how to prove such lower bounds. Okay, so because of that, we will not be able to solve things in spaces like order log n. Okay, so we have to use at least omega n space, but notice that m is at most n square. N could be n square or like order n square. So the natural thing we could ask is like, okay, what kind of functions, little of m functions we could have for the space bound. Okay, and so then we will ask like, okay, log n is not possible, then but n like m could be at most n square, but I want to solve it in less space, and how much less, and that should be little of m, right? If it is order m, I will be storing all the edges. Okay, and now since n is a lower bound for many problems, okay, the best possible we could think of is like theta and poly log n, because notice that to talk about a label of a vertex, I need log in bits. Okay, this is bits. Okay, so to talk about a label of a vertex, I need log in bits. So to talk about all the labels of all the vertices, I need how much? N log n bits. Okay, so if I'm allowed to use that much space, then can I solve interesting problem? So that is what the most of the study on the graph streaming algorithms are on. Like, so there is a lower bound of this bits like omega n.
No.
So
Oh, Shri,
we
move.
hope for
Beta.
okay then we go for n polylog n bits. Okay, so n is a lower bound, so it is a very good bound actually, n polylog n. If you think per vertex, you are going to store polylog n bits, and the label itself require log n bits. So if there is a lower bound of omega n, then it is a good bound for a space usage. Okay, and such kind of streaming algorithms are called the semi-streaming algorithms. Okay, so the graph problem where n is the number of vertices and the space allowed is like n polylog n bits, and such streaming algorithms are called semi-streaming algorithms. And for some problems, even that is not possible. Okay, so and like there will be some lower bound which says that that is not possible. You need at least omega n omega n log n, or even like some lower bounds of this form can also be proved. Okay, and like other interesting domains to study if this is not possible is like n to the power 2 minus epsilon for some epsilon, or like say like n to the power 3 by 2. I write O tilde. O tilde means polylog n is hiding there. So if you're not able to solve something on the space, space with using space n polylog n, then you try to solve it in to using space n to the power 2 minus epsilon, like better than brute force. Brute force in this setting is like storing everything, all the edges. Okay? But the important domain here is the semi-streaming model. So we will be mostly focusing on that semi-streaming model here. Okay? And is the definition clear? Like semi-streaming and streaming?
So can you repeat the second point, that what can we compute about G in little of in space?
Okay, see, for some problems, it may happen that I will not be able to come up with a streaming algorithm using n polylog n, n polylog n bits. Now, if you store all the edges in the memory, that takes order n square in the worst case. Okay, so you go for something between n polylog n and n square. So that is say n 3 by 2 is here. So you try to solve it using this much space. So if you are not able to solve something using this much space, then you try to solve it using slightly more space and try to prove lower bounds, like matching with that. Okay. So for some problems, we cannot even solve like better than n square minus epsilon for any epsilon, which that actually means that there is no streaming algorithm that solves that problem other than just storing all the edges. Like, so there is no streaming algorithm with a less space, like not even one less, asymptotically. Is that clear?
Yes, sir. Sir, and why do we call it semi-streaming?
Okay, because most of the numerical problems, like you have seen some heavy hitters, right? And then for the heavy hitters, we have seen this is the upper bound, right? Order log m, right? We can solve using order log m bits, where k, so assuming k is a constant. And most of the numerical problems we were able to solve using logarithmic in the input length. Log m, like using log m memory or order log m memory, we are able to solve most of the many of the numerical problems. Okay, and that is called as a streaming model. And in the case of graphs, that is not possible, like because there are like one can prove lower bound. So people just go on to what is possible, the best possible in that scenario. In that scenario, like you take n polylog n. Okay, so because of that, it is called a semi-streaming.
Okay.
Yeah, maybe like it is a streaming algorithm because the space usage is slightly higher. It is called a semi-streaming model, not like the not like the method of computation. Is that okay?
Yes, sir, thank you.
Okay. Now let us try to ask very basic questions on graphs, which is connectivity. Like one of them is connectivity. Okay. So think that G is given to you as a stream of edges, and at the end of the stream, you need to say like whether G is connected. Okay, or if it is connected, output a spanning tree. Okay, if it is not connected, then just say how many connected components are there, or output a spanning forest of it. Okay, and the other related problem is like minimum spanning tree. Okay, in the case of minimum spanning tree, the stream is of this form: E1 comma W of E1, E2 comma W of E2, like that, an edge and its weight. So a stream is given like this, an edge, its weight. Okay? And at the end of the stream, you need to output a minimum spanning tree of the graph. Okay? And another related notion about connectivity is k-edge connected. Okay, I don't know, maybe we'll not cover k-edge connected. Okay, but we will cover other two. Okay, so k-edge connected means like you like saying that is at the end of the stream you need to answer whether the graph is k-edge connected. What is the meaning of k-edge connected? You need to delete at least k edges to make the graph disconnected. Okay, so it is more connected, like connectivity is more. So maybe we'll not cover that in today's lecture because time is less, and we will cover other two and probably by part-time testing. Okay. Now, so the basic question, right? Given a stream of edges, so that will represent a graph, and at the end of the stream, I want to compute the number of connected components. Now, so I know n, which is v of g, and the edges are coming e1, e2, etc. up to em. Okay, and you are allowed, the space you are allowed to use is like order n polylog n bits. Okay, and at the end, like, so you will be reading like this from left to right, and you can use this much space. Okay, and at the end of the stream, you need to output the number of connected components. How can you do it? What is a simple algorithm? Can you suggest one? So the model of computation is given, like you have a restriction on the space usage, and at the end of the stream, you want to answer the following question, like the number of connected components. At the end of the stream, you need to output a number which says that, some number k, which says that the graph G has k connected, like the number of connected components in G is k. Can you think of an algorithm that does?
We can use a disjoint set. N bits. Okay, I'm sorry. We log n bits.
N polylog.
Yeah, so if we have a disjoint set where each vertex belongs to one component for every edge union of both those components.
So how do you process when you go from E1 to EM?
So, yeah, initially the graph has no edges.
Okay.
And there are so therefore the number of connected components is the number of vertices.
Okay.
Once we suppose U and V, two vertices are connected by edge E1, the number of components reduces by 1. That is basically a union operation on those two elements.
Okay. Yeah. Okay.
So
Okay.
perform union operations, ultimately count the number of distinct components. I mean, there will be n integers representing the n components that each of the vertex belongs to.
Okay. Yeah, that is correct. Okay. So the same algorithm in a slightly different words, I will explain next. Okay. So that is the correct method. Okay. So the thing is like maintain a spanning forest of the graph seen so far. Okay. That is what it does. Initially, like E1, E2, etc. up to EM. This is the edges. Initially, the graph is
Fahad?
like, you know.
Fahad?
Yeah.
So whatever he told this union find data structure, why will that be n polylog in space?
He will maintain that which all parts will contain which all the vertices. Like he will maintain sets. I guess that is what he said. Like you will have like initially n sets, and then
okay. Okay, so he's
and
going to
then
maintain
you will
sets.
have
Okay.
And that's what I
okay, then it's
understood.
fine. Okay, thanks.
So here at this point, V of G empty set. No edges are revealed to you. And at this point, it will be V of G E1. At this point, you have the graph V of G E1, E2. And like that, okay? So think that some of the edges are revealed to you, and that will make, till that point, you have a graph. And for that graph, you will be maintaining a spanning forest. What is a spanning forest? If the graph is connected, then a spanning tree is called a spanning forest equal to spanning tree. If the graph is not connected, then the union of a spanning trees of each connected, you pick spanning trees for each connected component and take the union, that is called spanning forest. Okay, so maintain a spanning forest. How do you maintain a spanning forest? The first time when E1 comes, you will add it. Okay, you will add to your spanning forest because first time when an edge comes E1, you add to your set F. Okay, so think F is a set of edges. Now I will tell what happens at the ith step. At any point in time, you have a forest, which is a spanning forest of the graph. So far you have seen. Okay. Now in the ith step, you will get an edge EI. Okay. And it has endpoints U and V. Okay. Now, if U and V are in different connected components, you add EI to F, and that will be a spanning forest for the graph which you have seen so far, including EI. And suppose EI is within a same connected component. If you look into the graph induced on F, then you discard it because already those two edges are connected within the graph induced on F, and the F you already keep, like already you have before EI comes, that is actually a spanning forest of the graph even after EI comes, like till that point. Okay, so this set F of like this set F, some set of edges you store. And how many edges will be there in a spanning forest? In a spanning tree, how many edges are there? It will be n minus 1. So you can try to prove yourself. If you have a graph on n vertices and which is a tree, then it will have n minus 1 edges. Okay, and so spanning forest means like a union of spanning trees of the connected components, which means that the number of edges in F is at most n minus 1, where n is the number of vertices of the whole graph. Okay, so you will be keeping only order n edges. Okay, and this set you can keep using order n log n bits. Okay, and at the end of the when the stream ends, what you output. So you maintain a spanning forest. What is
Number
the
of trees
output?
in the forest.
Yeah, number of connected components in the forest. Okay? You just output the number of connected components in the forest. Okay? So that will be same, right? Yeah, the definition of spanning forest says that the number of connected components in F as well as G are same. Okay? So this is a streaming algorithm, a semi-streaming algorithm for outputting the number of connected components. Yes.
So I have a question. So if I'm not wrong, this is exactly what union find data structure do.
Yeah. So it is written in a way that can explain the proof.
Okay. Okay. Thank you.
So what you said is like more like an implementation side argument.
Okay. Yeah. Thank you.
Okay. Okay. Now look at the next question. Suppose I want to output a minimum weight spanning tree. Okay. Assume that we are given a promise that at the end of the graph, like it is connected, and the edge stream, it is E1W of E1, E2W of E2. Like that is the way the edge stream is. Okay. And it is common in some order. Okay. And we want to process using the same space. Okay. Think that these space, like the weights can be stored using order log n bits. Okay. Assume that. Okay. So the weights are like integer weights between 1 and n. So you assume that. Okay? And then at the end of the stream, you want to answer the following question. Like you want to output the following: a minimum weight spanning tree. I hope you know what is a minimum weight spanning tree is. If not, please let me know. I assumed that. In case you don't know, you just type here, I will explain it. Okay, so you all know, okay? So how do we do it?
So by some order, we means in increasing order?
If it is in the increasing order, it is easy, right? You could use one of your algorithms which you have learned.
Okay, so they
right?
are coming in random order.
In some order, arbitrary order.
Okay.
Or adversarial order.
Okay.
And how can you solve it?
So
what will you do when the first edge comes?
So we'll keep adding the edges to the tree unless they don't form a cycle. And when a new edge comes, if it forms a cycle, we check it, we compare it with the edge that has maximum weight in the tree that we have already formed.
Okay. And then that you remove, right?
Yeah. And we add this to the tree.
Yeah. So that's a correct algorithm. Okay. So we are going to maintain a spanning forest as before, but like so it's not like the last edge comes which makes a cycle we will delete, but we will make a choice to what edge to delete. That choice we make based on the weights on the edges. Okay? When an edge EI with weight W of EI comes, and we check what happens when we add EI to F. If that is still acyclic, you add it. Okay. If that is not acyclic, then what you do is there will be a unique cycle formed using, like there is a unique path in F from U to V, and this additional edge EI will make a unique cycle. Okay? and look at the edge weights in it. Edge weights, or all the edges in that cycle, look at the weights of it. And one of them will have maximum weight. And for the ease of argument, assume that all the edge weights are distinct. Okay, so that will make proof easier. Okay, even otherwise it is correct, but to have a easier proof, assume that all the edge weights are distinct. Okay, then what you do is you will delete the maximum weight edge in that cycle. Okay, so delete that, and you can actually prove that that still is a spanning forest. Okay, and of the graph you have seen so far. And this is the process. And at the end of the stream, your output. Okay, at the end of the stream, what you output is, yeah, here I didn't write output, right? Say output V of G, comma F. Okay. Now, if G is a connected graph, then this will be a minimum weight spanning tree. Now we'll see a proof of it. Okay. Let T is equal to this graph, V of G, comma F, that is outputted by my algorithm. And if this is not a minimum weight spanning tree, like one assumption I make, all the edge weights are distinct. Now, if this is not a minimum weight spanning tree, then there is a minimum weight spanning tree T star. Okay, like some other edge, say F star and V of G. Right? And look at an edge E belonging to T star minus T. Such an edge exists because T star is a minimum weight spanning tree and T is not. If T is a minimum weight spanning tree, nothing to prove. So there is an edge E in T star minus E, T. Okay. Now, and we know that E does not belonging to T at the end of the string. Okay. When the edge E comes in that stream, you have decided one of them, right? You have decided either to include it in at that point in time, or you have decided to exclude it. Okay. So when you decided to exclude it, suppose you decided to exclude E, which means that there is a like let E is equal to EI. Okay, at the ith location E comes in, like in the ith E comes as the ith token, and let Fi minus 1 be the F value at that point in time, like soon after soon after you process the I minus first edge. Okay. Now suppose E you decided not to include in F, then what happened? What is the meaning of that? The meaning of that is like in Fi minus 1, there is a path, right? And this is what E is. And the weight of this edge is higher than all the weights in this path. Okay. Now look at your T star. Okay. And in that T star, you just delete E. And then you will get two connected components. T star is a spanning tree, which means that it is connected. When you delete E, you got two connected components. Okay, one edge deletion from a connected from a tree makes it a graph with two connected components. Okay, and look at this path. Like say I call it U comma V, and U will be here, V will be here because it will be in different connected components. And this path says that okay, there will be one of these edge like at least one of these edge which will be crossing here. And this side it is connected and this side it is connected. And what is that cost of this edge? Like say this is that edge, say E prime. That the cost of E prime is less than the cost of E. That is the reason you deleted E in the step I, which actually means that if you take T star minus E and then add E prime, then it will be a spanning tree. And what will be its weight? Its weight will be strictly smaller than the weight of T star. Okay, and that is a contradiction to the assumption that T star is actually a
Minimum spanning tree.
Minimum spanning tree. Okay, now there is the second case is like that is the first case. Okay? The second case is you actually included E at that point when it ended, or like when the ith token, that is E equal to EI, when the ith token arrives, you included it to F, and that become Fi. But it is not there at the end of the string because it is not there in T, which means that at some point in time you have deleted E. Let that be the point J. So when EJ come, you have deleted the edge E. What does that mean? When EJ came, at the time you process the jth token, it formed a cycle, and which edge you deleted? You deleted the edge E. Okay, and now look at this path. Okay, all the edges in this path has strictly smaller weight than E. And now follow the same argument. From T star you delete E and you will get two connected component. And from this path, the green path, which is between U and V, all the edges have lesser weight than E. And there is an edge connecting these two connected components. Like if I write here, this is what T star minus E, here it is connected, and there will be one edge from that green path that will be crossing here, because this, suppose U will be here, U is in this side and V is in this side, and this is a path, and this path has to cross, this partition at least once. Okay, so there will be at least one edge from this green path that will be crossing, and the left side is connected, right side is connected, and the cost of that edge E prime is strictly less than the cost of E. And again you do the same process, you delete E and include E prime, and what you will get is a spanning tree, and whose weight is strictly smaller than T star. And hence we proved that, like, we got contradiction when T is, like, if we assume that T is not a minimum spanning tree, then we reached a contradiction, like that T star is not a minimum spanning tree. Okay, and because of that, the output of the algorithm is a minimum spanning tree. Is the proof clear? If any of the argument is not clear, please let me know.
Yes, sir, it's clear, sir.
Okay. Okay, so I will not cover this K edge connectivity. So I will move on to the next topic. Okay. Okay. Now look at the next problem. Okay, which is like the edge stream comes, and at the end I want to test whether the graph is bipartite. Okay. When do you say a graph is bipartite? Like when the graph is too colorable, or in other words, whether if you are able to partition the graph into A and B such that all the edges have one endpoint in A and the other endpoint in B, then you say that the graph is bipartite. Okay, and it is a, you try to prove the following result. A graph is bipartite if and only if there is no odd length cycle. Okay, so I hope you know the definition of a cycle in a graph. Yes or no? Like if somebody doesn't know, then please just write -1. I will explain. So this is okay. Like just to be sure, like this closed walk is a cycle, whatever I wrote. But if I go like this is not a cycle. Like the green is not a cycle. So it should not have repetition. A closed walk in a graph and without any repetition of vertices and edges, that is called a cycle. Okay. Now, what is an odd cycle? An odd cycle is the one where the number of edges in the cycle like is an odd number. Okay. Now, so we want to test whether a graph is bipartite or not. Okay. Now, again, using a streaming algorithm, right? So we semi-streaming algorithm. So we are allowed to use space order n polylog n bits. And the edges are coming like a stream E1 to EM. And at the end, we need to say yes if the graph is bipartite and no otherwise. Okay. So this proposition you try to prove yourself. G is bipartite if and only if there is no odd cycle in G. Okay. Now, how do we prove that? Okay. Okay, now I wrote here, is there a sparse certificate exists there? Okay, now in the case of minimum spanning tree, what you have stored in the memory, that is a sparse certificate for your question. So in a streaming algorithm, what you actually store in a memory will play a role for a sparse certificate to answer the question. Okay. Now, towards explaining that, I will define something called a bipartite double cover. Okay, a bipartite double cover of a graph G. Okay, of any graph, not necessarily bipartite graph. Okay, G is any graph. A bipartite double cover is defined as follows. Okay, so maybe I will explain using an example and then the formal definition. For every vertex, you take two copies. One is the white copy and the other is the red copy. Okay, this is the copy 1, this is the copy 2. Copy 1, copy 2, copy 1, copy 2, copy 1, copy 2. Okay, now, and if there is an edge between two vertices, say UV, okay, the U vertex in copy 1 to V vertex in copy 2, you add an edge. And similarly, U vertex in copy 2 to V vertex in copy 1, you add an edge. Okay. So for every vertex U, you have two copies. A red copy, call it, the first copy. And a white copy, call it the first copy. And a red copy, that is called the second copy. And for every edge UV in G, you add edge like, between their copies, like between their, classes, like from the white class to red class and red class to white class. So for one edge, you add two edges in D of G. And this D of G is defined for any graph, not necessarily for bipartite graph. And it is easy to see that D of G is a bipartite graph because all the white copies on the left side you write and all the red copies you write on the right side, then you can see that all the edges are crossing between white and red. Okay. So it is a bipartite graph. Okay. Now, so this is what like a G here and I wrote a D of G here and a G prime here and I wrote a D of G prime here. Okay. Now, in this example, let's just closely look into this example. And one of the G is a bipartite graph. Which G is a bipartite graph? Like one of the graph is a bipartite graph. Like, of course, D of G will be a bipartite graph because it is a double cover. G and G prime, which is bipartite and which is not bipartite.
Sir, can you explain how the red and white graphs are formed again?
Okay. So I have a vertex, V here, right? And say I have a vertex U here. Okay. For every vertex V, I have two copies. It's white copy and it's red copy. Say call it V1 and call it V2. And similarly for U, I have like U1, U2. U2 is the red copy and U1 is the white copy. And there is an edge in the graph, what it is, VU. Okay, this is VU. Okay, VU. Okay, then I add from an edge from V1 to U2 and V2 to U1. Is that clear now?
Yes, sir. Thank you, sir.
Okay. And notice that the D of G is bipartite because all the white you put on the left side and the red vertices you put on the right side, then all the edges will be from white to red or red to white. Okay? So it is bipartite. G prime has a Horde cycle, hence not bipartite, but G is a bipartite graph. Okay, so this is a bipartition. And what is the difference between D of G and D of G prime?
Second one is connected.
Yeah, second one is connected, and the first one not connected.
Yeah.
Right? First one is not connected, second one is connected. Okay. Now, okay, and that is the property we use. Okay. Now, like look at G, if G is connected and it is a bipartite graph, and then look at D of G. How many connected component there you see? You will see two connected component. Okay. And suppose G prime is a connected non-bipartite graph, then D of G prime is actually a connected graph. Okay, so the number of connected component here is same as the number of connected component here. Okay. Okay, so what we claim is G is bipartite if and only if the number of connected components in D of G is equal to 2 times the number of connected components in G. Okay, so okay, now suppose, okay, now it like, so what we like what we could prove is, like, suppose G is connected, then the number of connected component in D of G is 2, and if G, if G is connected and it is bipartite, then the number of connected component in D of G is 2, and if G is not connected, if G is connected and not bipartite, then the number of connected component in D of G is 1. And using that, like that you apply for all the connected components in a given graph, you will get what I said. Okay, take G is a graph. If it is bipartite, then the number of connected component in D of G is 2 times the number of connected components in G. And if it is not bipartite, then the number of connected components will be same. Okay, to prove that, if you think a little bit more, then you will see that if I prove the following statement, this statement will be true. Okay, so for that you need to just make a close look on how this D of G is made. Okay, suppose G is connected and it is bipartite, then D of G has 2 connected components, and suppose G is connected and not bipartite, then D of G is connected. Okay, now if this is given to us, then what we can use, we can actually run the connectivity sketch, which you have seen how to solve the connectivity, like how to say the number of connected component in the graph, like which we have seen as a first example, like that you apply to D of G. The only thing is that your actual stream is, E1, E2, etc. up to EM. Okay, so when E1 comes in D of G, there exists two edges. Like one is like for two, there are two edge copies corresponding to an edge E1. So you can think that each edge in the original stream replaced with two edges in the stream for D of G, and you keep the same as a connectivity sketch, which is a spanning forest for D of G, and at the end you will see whether it has two connected components. Or what you can do is, for the general problem, for both G as well as for both D of G, you will be keeping a spanning forest in a streaming fashion, and at the end you will test whether the number of connected component from the sketch of D of G is twice the number of connected components of G. If that is the case, you output yes, otherwise you output no. Okay, so you can try to think about that algorithm, how to implement it, like, and I will move to the proof. Okay, so if we are going to keep connectivity sketch for G or D of G, G as well as D of G, how much space we will be using? Order n log n, because the number of vertices in D of G is 2 times n, and a spanning forest will contain at most 2n minus 1 edges. So the number of total number of edges you will be keeping for the connectivity sketch of G union the connectivity sketch for D of G will be at most 3n minus 2. So that information you can store it in space order n log n bits. Okay, now we are going to prove that statement which I said. Okay, so I will take 3 minutes and we'll prove it and then stop. Okay, so suppose G is a connected graph and G is bipartite, then D of G has two connected components. Okay, the proof is very simple. Okay, G is a connected graph and it is a bipartite graph. What is the meaning that it is a bipartite graph? It can be partitioned into, A comma B, and all the edges are here. Oh, sorry, maybe I write here. All the edges are here. Okay, and now how did you construct a D of G? D of G has a, white copy, not white copy, I make it yellow copy. Okay, this yellow copy, and there is a red copy for every vertex. Okay, and look at that partition in both the copies. And since the edges are between A and B, how does the edges look like in D of G? Like this part is, D of G. It will be looking like this. Look at the graph induced on, this. This will be identical to G, right? And similarly, look at the graph induced on this part. This will be identical to, like, isomorphic to G. Okay. And will there be any edge between this blue and purple?
No.
No, there is no edge between this blue and purple. And since this is isomorphic, like this blue part is identical to G, that G is connected, which means that how many connected components here? Two connected components. There is no edge between, the purple mark, the vertices marked purple and the vertices marked blue. Okay, and the vertices marked purple, like if you look into that graph, that will be like identical to G. Like it will be isomorphic to G. Like, because here it is a copy, here it is a B copy, and you add edges according to what is there between A and B. Is this argument clear? If not, I will explain it again. Yes or no?
Yes, sir. Clear.
Okay, so if G is a connected graph and it is bipartite, then the number of connected components in D of G is 2. Okay, now we prove the other direction. Okay, which actually means that G is connected and G is not bipartite. Then D of G is connected. Okay, now suppose, okay, I will explain it through an example, and then that can be extended. Okay, suppose G is not bipartite. What does it mean? It means that there is an odd cycle. Okay, so let the odd cycle, I write it U, X, Y, Z, W, and U. 1, 2, 3, 4, 5. Okay, now what I claim is, say U1 and U2. These are two vertices in D of G, right? The copies of U, U1 and U2 belonging to U are connected in D of G. How to see they are connected? Look at U1. From U1, there is an edge. From U, there is an edge to X, which means that from U1, there is an edge to X2. From X to Y, X to Y, there is an edge in G, which means that from X2 to Y1, there is an edge. And Y to Z, there is an edge, which means that Y1 to Z2, there is an edge. The copy into Z. Okay. Z to W, there is an edge, which means that W1, there is an edge. Okay. And W to U, there is an edge in G, which means that I will be adding an edge like this. So U1 is connected to U2 in D of G. Okay. And this idea you can extend with any odd cycle. It's like it just shifts between 1 and 2, right? And if the length is odd, then you will reach U2 using that odd cycle. So U1 and U2 are connected in D of G. And next we claim that for any vertex A in D of G is connected to either U1 or U2. Okay. Now, since G is connected, A is connected to U in some way, right? So A is connected to U. Say A is connected via B, C, D, and U. Okay. Then what you can do is like, any vertex, say, I call it A1. Okay. Say for any vertex A in B of G, A1 belonging to D of G is connected to U1 or U2. Similarly, A2 belonging to D of G is connected to either U1 or U2. Okay. Now look at this path, A to U in G. Okay. Now from A1 I can go to B2 in D of G. From B2 I can go to C1 in D of G. From C1 I can go to D2 in D of G. And from D2 I can go to U1, which means that A1 is connected to U1. And if I take that as A2 I can go to B1. And from B1 I can go to C2. This is in D of G. And C2 I can go to D1. And from D1 I can go to U2. Which means that every vertex in D of G is connected either to U1 or to U2. And U1 and U2 are connected, which means that the whole graph D of G is connected. Is that argument clear? U1 and U2 are connected in D of G, and every vertex in D of G is connected to either U1 or U2, and hence D of G is connected. Okay, and this I explained using a symbol like a 4-line path. You can take any length path and you can extend that to either to U or to U1 or U2. And so that is what the proof for the other direction. If it is not bipartite and connected, then D of G is actually a connected graph. Okay, and this is formally written proof. And that's all. Like, do you have any question about the last proof? So we have seen connectivity and bipartite net testing. Here we also see MST, all in semi-streaming. Okay, then see you tomorrow.